Okay, so with what Chris described, we're now at the point where we can optimize a neural network inside of our shading code. This is quite neat, but if you look at the end result a bit more critically, well, this doesn't actually look all that good, right? If you actually wanted to use this, the output quality of this network is pretty far from something you would actually want to put on the screen. Now, generally, the quality of a network will improve as you add more parameters. We've already seen this in the previous section when Chris showed you adding additional layers. So let's see if things will improve if we just add more neurons or more layers. So currently we use 3 layers of 32 neurons. So let's try making them 64 neurons wide. Things are a little better, so let's try adding another layer. Okay. So what we're seeing here is that as we add more capacity to the network, the output does improve. And in fact, if we add enough parameters, in the end, the network will be an almost perfect fit for our input texture. This isn't just true for textures, but neural networks can approximate pretty much any function almost perfectly as long as you give it enough parameters and enough training data. The main caveat here is, of course, that we have things to do. We can't just add as many parameters as we like. At the end of the day, we want this to run in real time. So there's actually a pretty hard limit to how big we can make the network. So it's a pretty valid question to ask. Is this even practical for real-time rendering? For networks that are small enough that we can run them in real time in our graphics pipeline, at least in this texture example, it doesn't look like you can actually get usable quality out of them. Now, this is the point where people sometimes stop exploring this approach altogether because it just doesn't look practical. But the point I want to drive home in this section is that there's actually a lot more you can squeeze out of these small networks. And I would actually argue that in graphics, this is a situation that we've seen before. I don't know if you've heard this statement, but Monte Carlo ray tracing or path tracing can render pretty much anything, right? You can throw away your shadow maps and your light probes because path tracing can handle any scene and any lighting that you throw at it. But then you try it and realize that, yes, eventually you will get a usable result if you give it enough rays per pixel. But for your real-time budget, you just can't seem to get anywhere near usable quality out of it. Well, ray tracing is shipping, because this isn't actually true, right? We can get perfectly usable images out of it. We just need to be a bit more careful with how we use our budget of rays. For any universal, in quotation marks, tool like ray tracing or neural networks, once you actually care about efficiency, you have to use it more carefully. And so for real-time ray tracing, we already figured out a lot of the components for this, right? Today we have DLSS and restir and path guiding. So let's talk about some tools you can use for neural shading to use your budget of parameters more carefully. So let's debug what's going wrong here, right? Well, so the first thing you'll notice when you fire up the training example is that this actually runs quite slow. And the reason for this, in part, is because we use the same strategy as we used for the bitmapping example, and we evaluate the loss sort of exhaustively for every pixel in the texture. This was necessary when we had to actually optimize a separate value for each texel in our bitmap, but we don't actually need to do this anymore once we have a neural network, because we have one set of parameters for the whole texture. So regardless of where we evaluate the loss, we get some information that propagates back to the whole texture. And so a better baseline might be pick a much sparser set of points, but then you'll end up with these structured artifacts. So a good baseline to do would be something like randomly picking a small set of points in a texture to evaluate the gradient and then run your optimization loop. The gradients are now noisier, but you get many more optimization loops for the same training budget of time, that is. And so in the end, you'll end up getting better results out. Now, an even better baseline might be to sort of be more strategic about how you distribute your samples. Maybe instead of uniformly generating random points, you might want to sort of generate a jittered grid, so you have at least one training sample for each sort of square in your texture. But let's try to do the simplest thing right now and run it. And this already is much better. At equal time, you end up optimizing quite a bit faster. Now, something that you see here is that as the texture gets close to converging, this thing looks a bit twitchy. It looks a bit jittery. And this is because our gradients are now noisier. And so an even better thing to do would be to sort of slowly increase the size of your training batch, the number of training samples over time, so that as you get closer to convergence, your gradients are less noisy. Now, a more egregious thing that you might notice is that every now and then when you fire up the training example, the training seems to get sort of weirdly stuck in a weird state. It sort of has a bad initialization. The initialization of the parameters is random. And every now and then it gets unlucky, and the texture is so bad that it seems to not actually learn anything useful. It looks like it's stuck. And this seems weird, right? Because we tell it to minimize a certain loss, but it doesn't seem to actually make progress for it. Now, the main culprit for this is actually our choice of activation function. The thing that we described in the previous section that Chris talked about, is this simple clamp, is something that's called a ReLU activation. And it is effective, but one main drawback that it has is that when the output of a network layer is negative, well, the value is clamped and the activation there is flat. That means the derivative, the gradient, is 0. If you're particularly unlucky with your initialization, and for any input, the output of the network layer is negative, well, all of its derivatives are 0 all the time, and it never receives any updates at all. It gets stuck in this initial state and doesn't progress. Luckily, there's an easy fix for this by using what's called a leaky activation that still has some gradient, just a small one when it gets negative. And the simplest version of this is called the leaky ReLU, where instead of clamping to 0, we just scale down the input when it's negative. This is a very small change, but this more or less completely removes the stuck state. Now, the next thing that you'll notice is that the output of the network, it looks weirdly like it's triangulated, like it's made of these little pieces that almost look like they're linearly interpolated. And this is because that's actually true. That is what happens. This is again because of the activation that we use. If you use ReLU, then your network can only ever produce outputs that are piecewise linear. We can do a little bit better by using a smoother activation at the output. A nice thing to try is an exponential, because it's very nice and smooth, and it also happens to be leaky. Even when the input is negative, you still get gradients. And so putting all this together, this is what we had before with just a simple ReLU for each activation. And now using leaky ReLU for the internal activations and an exponential at the output, we get a network that always converges to something useful, and the output is a little bit smoother. You can still see there seem to be some concrete regions where individual neurons are active, but they're no longer quite linearly interpolated. Okay. So this looks better, but we're still quite far from a useful texture as output. So clearly something needs to improve. And we can get some insight into what's going on by thinking a bit more deeply about the problem that we're asking the network to solve. We want it to act like a texture, meaning that we feed it UV coordinates and we ask to get the texture color out. And if you visualize this sort of over the whole space of the texture, essentially what we're doing is we're giving it two image gradients going from black to white for U and V, and we're asking it to turn that into the image on the right. And so in a way, it shouldn't be surprising that it struggles to do this well, because this isn't actually how we normally do image representation, right? When you build an image codec or a compression method from scratch, you would use much more complex building blocks to create your image than simple gradients. If you did JPEG, you use a collection of cosines. You might use wavelets, or for compressed textures, you might use BC6 or BC7 blocks, and so forth. And, well, if we give the network enough parameters and enough training data, then it turns out eventually it will learn or discover something very similar. It will learn its own building blocks. But for a small network, it's actually very wasteful to do things this way. Why are we asking the network to use its very limited parameters to learn something that we already know how to do, these sort of building blocks for images? So let's try giving the network some more useful inputs that are sort of loosely inspired by JPEG. In a way, we're distilling the existing knowledge that we have about image compression into a fixed function block that's fed to the network, and only have the network learn the rest. I didn't come up with this. This is something called a frequency encoding. And so what it means is that instead of giving the network just the u and v coordinates, we first pass u and v through sines and cosines, sine and cosine functions, at different frequencies. And then we give that to the network. And so instead of constructing an image out of a UV gradient, you can construct an image out of sort of different frequencies of sines and cosines. And this is what we get when we switch to this input encoding. And this is a pretty dramatic improvement without actually costing very much. We didn't add, a huge amount of extra parameters or, add in a really expensive thing. It's just adding a slightly more useful input to the network. In fact, this network just has 3 layers and 32 neurons. And if you compare this with the naive network that we started with, well, with the same number of parameters, you can see there's actually a pretty big quality difference between the two, just by being slightly smarter about what we do inside the network, which activations that we use, and what inputs that we pass to it. You could take this even further and make the input encoding trainable as well. Of course, we don't want to make the input encoding a neural network. That will just land us back where we started. But you could replace it with something that's learnable, but in a more efficient way than a network. For example, by replacing the sines and cosines with a small texture of input features that you train alongside the network. Implementing this is actually very simple. We already know how to optimize bitmaps. And in this case, instead of passing in sines and cosine, we just sample this texture in a differentiable way and then feed that to the network. And so if you do this and train it, well, you get an end result that eventually gets extremely close to the reference. On the right, you can see the texture that it learns. This texture doesn't contain colors in the traditional sense, but it learns, some abstract numbers that the network uses to generate texture colors in the end. Usually this is something called a latent texture, and it contains what are called latent codes. Now, of course, this latent texture has to be smaller than the texture that we're learning in terms of resolution. Otherwise, we're just transforming a 256 by 256 latent texture into a 256 by 256 texture with some complicated network in between. That's not very useful. And in this case, the latent texture is actually 32 by 32, and the network turns it into this 256 squared output. So in a way, the network now acts as a sort of learned decompressor or upsampler, but still the output quality is dramatically better than what we had before. Now you could go even farther, for example, by using some hierarchy of latent textures, and they might not have to be full bit depth. They might be really low bit depth, like 4-bit or 2-bit. But I'm going to stop here because, of course, the point of this section is not actually to build a state-of-the-art neural texture compression. In fact, there's a section later in the course that goes more into doing that. But instead, I wanted to drive home some takeaways that are important if you want to be productive in neural shading in your workflow. The first one, and we saw this here, is that if you use small trainable models, then really they need careful engineering if you want them to work well. For example, this can mean to not make them learn things that you already know how to do. Or, much like every tool in graphics, you need to build up sort of a mental toolbox of common optimization tricks to try, like different architectures or optimizers or activations, pre-processing your data, and so forth. And you'll have to build up some intuition for how to debug things when they don't work as expected. The tricks that I showed you don't work in every case. The solutions might vary depending on your application, but these are some things that are useful to try. Now, some of this stuff that I just recommended actually runs counter to good practices in modern machine learning. This is because a lot of the problems that we saw just go away when your model has billions of parameters. You don't need to feed it a good encoding of the inputs if you have enough parameters to sort of rediscover image compression. And so it's important to keep in mind that we're in an entirely different regime of network behavior compared to the really large models that people train nowadays. And some of the advice that you read online for large models might not apply to small models. The other thing that I really can't stress enough is that in order to be productive in neural shading, your code has to be fast to iterate. And I don't mean that the main loop has to run really fast, although that helps also. But really, I mean the loop that involves you and the code, where you iteratively change it to try new things, to try and improve the network behavior. And that's because whenever you try to solve a new task with a trainable model, you rarely get something that works perfectly out of the box. And likely you'll have to experiment with a bunch of different ideas and training tricks, and they might dramatically transform the code that runs your model or does your training. And anything that stands in the way of doing that might stop you from succeeding, because it will take that much more effort to run each experiment, and you'll get so many fewer iterations done. And if each time you have to rederive and manually code your backwards derivatives, or if every time you change the model you have to write a bunch of boilerplate for setting up your pipeline or for creating and binding new buffers or loading new shaders, you're much less likely to get to the experiment that will actually point you to success. And I speak from experience because we felt this pain when we started writing our own neural shading applications. And this is in part why we built the Slang ecosystem that includes automatic differentiation and SlangPy for rapid prototyping with Slang in Python. Now, it might sound weird to put Python and real-time in the same context, but Python happens to be very friendly to this kind of rapid exploration, where you might need to make frequent changes to how your training code operates. But once you've found a model architecture and training setup that works, you can go and develop it in C++ to get all the performance out of it that you want. The important piece is that the core logic, the shader code that actually runs your neural model and evaluates your training code, doesn't have to change between Python and C++, and they can be shared between the framework where you prototype in and the one where you ship your code in. And this is a big advantage compared to using something like PyTorch or JAX, which live in an entirely different world from your renderer and need you to rewrite everything from scratch in their framework when you actually want to sort of train it, compared to where you want to ship the thing in the end.